Hi, my name is Dale Rhoda with Biostat Global Consulting, and I'm recording this video to share the presentation that I gave at the AAPOR conference in Los Angeles in May of this year. We're looking at what are the consequences of using smaller and smaller cluster surveys to measure vaccination coverage in low and middle income countries. I want to acknowledge the important contributions of my colleagues who are listed here. We did this work in collaboration with our colleagues at the Aga Khan University, who contributed the data that forms the basis of the simulations that I'll talk about today. The context that we're considering is surveys to measure vaccination coverage. And as you know, vaccination is one of the most effective public health interventions known to mankind. In low and middle income countries, there are administrative systems for tracking the number of doses who are given to kids, but those administrative systems do an imperfect job of quantifying vaccination coverage. And so from time to time, we conduct household surveys to give independent coverage estimates. For decades now, the World Health Organization has given resources to help design and execute those surveys. And my team has had the privilege of assisting WHO in updating and assembling those materials, both back in the 2018 manual, which appears here in the lower right, and for an update even to that manual, which will appear later this year in 2026. Vaccination coverage surveys typically use a multi-stage stratified cluster design. In the best cases, there's rigorously random selection at every stage. The WHO materials recommend that each survey stratum should have 30 or more clusters in order to estimate coverage well. And for those who don't know, the target population for this work are children who are exactly 1 year old. They've had their first birthday, but not their second birthday. We visit the home, ask the caregiver some questions, ask to see that child's immunization card, the home-based card, which you can see here in the hands of these moms. This is the day in Bangladesh when these kids receive their cards, and they should be kept by the caregiver in the home. And if the caregiver doesn't have it, then we ask them to recall what doses the child might have had. And in some cases, we go to the health facility to look up the child's record to learn what doses they have and have not received. These surveys like to report outcomes at the national level and the first subnational levels. These are the levels where outcomes are commonly reported in international standardized surveys as done with the demographic and health surveys or multi-indicator cluster surveys. But the health program is administered not at the first subnational level, but at the second or third subnational level in something called health districts. And so the stakeholders would like very much to know what is coverage in district by district in order to administer their program. Some countries stratify the larger surveys to be sure that there are at least, say, 5 clusters per health district, partly for the purposes of being sure that all the districts are represented and when the numbers are rolled up to provincial or national levels. That stratification, that inclusion of data from each district sparks a natural question from the stakeholders. They may say something which I'll paraphrase with the words on this slide. Yes, we understand that technically it's good to have 30 or more clusters in order to estimate coverage, but since we have data from kids from each district, couldn't we please report design-based survey outcomes at the district level in cases where we've used 5 or 10 or 15 clusters? Because our program managers would really like to know how things are changing at the district level. They'd like to understand where are the vaccination levels and how are they changing from year to year. And so the question from the stakeholders back to us as survey methodologists is, what would we risk if we reported outcomes from fewer clusters than is technically recommended? That's what we're going to look at in this talk today. Our approach to give some insight to that question is to use simulation studies. We have 28 faux populations that I'll show you in a moment. They're inspired by real data from across Pakistan. And we're going to try to answer the question at a variety of coverage levels and for a variety of coverage heterogeneity levels also. So that's why we're going to use 28 outcome scenarios, 7 different outcome levels and 4 different levels of heterogeneity, so that we can say something about how the answer varies across the spectrum of outcomes that we see here. And we're going to, having set up those faux populations, which I'll go into more in a moment, we're going to sample them using 5 designs that are real world designs that are used in various countries for various purposes. And so those designs are listed at the right. The first design is used in the Democratic Republic of Congo, where they do surveys with 5 clusters in each district and 30 kids per cluster. The next 2 designs are 10 clusters by 12 kids and 15 clusters by 12 kids. Those are used in SHRUC surveys, super high risk union councils, where the data are aggregated up across union councils to higher levels for reporting purposes. The classic World Health Organization cluster survey design is 30 clusters and 7 kids per cluster, so we want to include that classic design. And then recently, in 3 different rounds of surveys in Pakistan, there's been substantial investment in what's called TPVIX, Third-Party Verification Immunization Coverage Survey, where some districts had 49 clusters and some districts had 64 clusters. And in both cases, we're looking at a target of 12 kids per cluster. So we want to see what happens when we use these different designs. What is the sampling variability like? We'll look, first of all, what is sampling variability like for just a single cross-sectional survey? How much do the point estimates from these samples vary from what we know is the true underlying district level coverage? And then we'll try to empathize with the district level program managers. We'll look at what would happen if we sampled, let's say 3 years in a row. We provided a time series of 3 outcomes to see, do the point estimates provide patterns that might inspire some programmatic action, and are those patterns and actions appropriate? So we're going to look at, in the trend analysis, we're going to look at 2 scenarios. The first scenario is in the bottom left here. Maybe we've got circles, yes. There's no underlying change. So although the program manager doesn't know it and the survey results may not reflect it, we know that the underlying population we're sampling from, there's no change from year to year to year. And then there are many other possibilities. We could look at situations where coverage stays flat and goes down, flat and goes up, et cetera, et cetera, et cetera. In the interest of time, we're also only going to look at this complementary scenario at the end where, again, the program manager wouldn't know it, but we know because we are wrangling the data that are being sampled. We know that the underlying coverage, the true coverage, is going up by 10% each year. And so the question is, what do the patterns, especially in the point estimates, show? Do they reflect reality for those program managers? That's what we're going to look at. Here's what one of our 28 populations looks like. These are data from a real survey in Pakistan with dozens of clusters. Each column here, each tiny column is a cluster from that survey, and the height of the color bar here is the portion of kids in that cluster who were observed to have the outcome of interest. So there were 4 clusters where every kid in the cluster had the outcome of interest. There were almost 10 clusters where none of the kids had the outcome of interest, and then there are all manner of results in between. So we take this is a sample, but for our purposes today, we treat this as the population. That we say that coverage across this district is distributed like this, and then we're going to draw samples from this, maybe 5 clusters, maybe 10, 15, 20. We'll do bootstrap samples from a population that is defined by this sample. Because we are defining this now as a population, we know that the true answer is that 49.3% of the kids have the outcome of interest here. And the intra-cluster correlation coefficient for this sample was 0.37. Here are all 28 of the populations that we're interested in. This figure on the left is plotting estimated coverage, so from 0 to 100%, versus intra-cluster correlation coefficient. And these are observed values from the first 2 rounds of Pakistan TPVIX. You can go to this link and explore these data in more detail. I've selected 7 levels of outcome indicated by the columns here. And for each level of outcome, I've selected 4 levels of heterogeneity, or 4 levels of intra-cluster correlation coefficient. I've pulled out the sample from the TPVIX data sets. They look like these. These are the organ pipe plots. So the first four have very low coverage, around 4 or 5%. Then we go up to about 27, 28%, around 40%, 50%, 62 to 3%, 80-ish%, and then 95-ish% of the kids with the outcome of interest. So in our simulation studies today, we're trying to show you what would happen if you used small, medium, and large number of clusters, and we're trying to show results across the coverage spectrum and for a variety of values of realistic intra-cluster correlation. Each of the figures for the rest of the talk will be laid out in this format of 7 columns and 4 rows. So just remember that as we go from left to right, we go from low coverage to medium to high coverage. And as we go from the bottom row to the top row, we're going from extreme homogeneity, where the intra-cluster correlation coefficient is very low, meaning that there's very little variability from cluster to cluster. And then as we get higher, the ICC goes up. This is more heterogeneous outcomes. Great. Okay, this slide is showing, again, we're in the 7x4 outcome pattern here that we'll see for the rest of the talk. And here we're showing when we draw hundreds of times from those distributions, how far do the point estimates from our sample draws, how far do they fall from what we know is the true coverage in that cluster? And the green bits are simulations that fall within 5%, and then yellow is within 10%, et cetera, et cetera, et cetera. The black mean that the sample, the answer that we get from we would estimate from the sample is 20% or more from the true answer. And so we see here that when heterogeneity is low, that's in our low row, for homogeneous samples, and a large number of clusters, 64 clusters, the sample answer rarely falls far from the true answer. These are very tight distributions here. The observations are all stacked on top of each other. And that as we go down in the number of clusters, even when the population is homogeneous, the answers that come out of the simulation can be 5, 10, 15, and even 20% from the truth. And then if you take a step back and hold this at arm's length, you see that as we go up a row, everything gets a bit wider. Up another row, things get pushed out again to the left and to the right. And for the cases where the intra-cluster correlation coefficient is around 1/3, about 32, 33%, we see here that especially for low numbers of clusters, there can be many observations where the sample coverage estimate is 10, 20, 15, or more percent from the truth. The sampling variability is high, and so the point estimate alone can be quite misleading. In this representation, we've stacked many observations on top of each other. If we want to say, well, what percentage of the observations are stacked here in green? These are the same outcomes, but now we're showing them spread out in a stacked bar chart. So we see here that with 64 clusters and low heterogeneity, even when coverage is 50%, which is where things are most variable, nearly all of the samples are within 5% of the truth. And then as we go down in the number of clusters here, we get to the point where with only 5 clusters, only half of the estimates are within 5% of the truth. And then as we go up in heterogeneity, and this is a pattern we see over and over again in these results, as we go upward in the rows, things fall farther from the truth more of the time. And so in this case, with 5 clusters at 50%, it's only about a quarter of the outcomes that are within 5%, only half are within 10%. So this is saying that with 5 clusters, ICC of 0.32 and coverage of 50%, half of the observations are going to be more than 10% away from the truth. But you don't know, for looking at any particular survey outcome, whether you're within 5%, 10%, or whether you're 20 or more percent points away from the truth. The good news is that confidence intervals work, except for at the left and right extremes, where we know confidence intervals for proportions have some struggles. Everywhere in the middle, 95% of the confidence intervals contain the true answer. So the confidence intervals are going to be wide in some cases, but the true coverage value is in fact inside the 95% confidence interval. So the lesson from this slide is that if you report coverage using a small number of clusters, you shouldn't report only the point estimate. You should calculate a survey adjusted confidence interval and report that also. And if you do that, the true answer is likely to be within the confidence interval, where the only challenges then are for extremely low coverage figures and extremely high coverage figures. Now let's look at what happens in repeated draws. So the first situation is going to be where the underlying population doesn't change. We do 3 draws from it and look to see what's happening to the point estimates. In this is showing what portion of the pairs have an apparent change that's bigger than 5%. The absolute value of the difference between draw 1 and draw 2, or draw 2 and draw 3, is 5% or bigger. It should be 0. Nothing actually changed. But we can see here that most of the time, for most of the designs that have 30 or fewer clusters, the change looks like it's more than 5%. The next slide shows us for 10%. So again, using a small number of clusters, it's still the fact that more than half of the time, for 5 clusters, more than half of the apparent changes look like they're 10% or more, even though the true coverage did not change. So 10% is an important threshold. I would think that in many cases, the program managers would think, hey, if we're seeing a 10% change from year to year here, that's probably real. That's probably reflecting something that's happening that's in the underlying population. Here's the proportion that are greater than 20%. With 5 or 10 clusters, with 5 clusters, it's still half the time you would see an apparent change that's 20% or more for one of the pairs, and for more than 10% of the time, you would see an apparent change of 20% in both of the differences. Both changes would look like they were 20% or more, when in fact the underlying coverage didn't change. So this is pointing out the fact that looking at a time series of point estimates using a small number of clusters can be misleading. These should be all green if we wanted to know the truth, but we're seeing a lot of misleading apparent changes. So that's the situation when we have static population. Again, confidence intervals and hypothesis tests work. If you did a formal statistical hypothesis test for whether things change from one round to the other, the tests account appropriately for the fact that you have a small number of clusters, and only about 5% of the tests would give a statistically significant result. That's the alpha of 5%. We expect 5% of falsely significant results, even if nothing is changing. So this would indicate that if you're going to report changes, not only if you're going to report coverage, you should report the confidence intervals. And if you're going to show apparent quote unquote trends over time, you should also calculate a formal survey adjusted hypothesis test for whether things changed or not. Because even when the change is apparently high, the hypothesis test is likely to give you the true answer that in fact we don't have strong evidence of an underlying change there. So that's a really important result on that slide. Now let's go to the last scenario here, where we, as the controllers of the data, are making the coverage go up by 10% each round. And here's how we're doing that. The yellow portions here are what we saw in pink before. That's the round 1 coverage. And then green is round 2. So we bump the coverage up in every cluster such that overall coverage goes up by 10%. And then in the third round, we bump it up again to these blue levels. Of course, at the high end, we only had room to bump things up by 10% once then we had reached 100% coverage. But everywhere else, we had room to go up by 10 and then by nearly 10 again. Now we're going to look at change from round 1 to round 2. The true change was 10%. I'm coloring the bars green here if the apparent change was positive, and if it was anywhere from 0 to 20%, I'm saying, all right, that's not super misleading. But in red, I've colored the portion of the changes that look like they're negative. The true coverage went up by 10%, but the point estimates make it look like coverage went down at least a small bit. That's misleading, so I've colored those red. Similarly, if the point estimates make it look like it went up by 20% or more, I'm calling that misleading also in a different way. It's showing an increase, but it's really inflating the increase. Those are colored yellow. You can see that here that near the top of the figure, in the middle, about half of the time you have a misleading result in one direction or the other. About half of the misleading results are showing a decrease in coverage when it should have shown a 10% increase, and about half of them are showing 20% or more increase when the true increase was only 10%. So as you can see that within any box here, as you use more and more clusters, we get more and more green, more and more of the pairs would be what I'll call not misleading here. And as we go to fewer and fewer clusters in any of the boxes toward the center of the figure, more and more of the pairs would be puzzling, misleading, and perhaps inefficient. If things look like they've gone in a negative direction, there might be some programmatic consequence there. If things look like they've improved by more than 20%, there might be some unwarranted celebration, promotion, rewards, and then continuing what's going on there. This is showing the net change over 2 rounds. So now coverage changed by 10% and then it improved by 10% more. So the net change should be 20. So I have generously colored anything between 0 and 40% signal in the point estimates as green here. But again, if the true change was a positive 20 and what we appear to see is negative, then I've colored it red. We can see about 10% of the changes up here are negative. And then if it appears to have improved by more than 40%, that's twice the true change. I'm calling that misleading in another way, and we've colored it yellow. And again, with an ICC of 1/3 and coverage in the middle, we see sort of maybe 10% of the outcomes are misleading in one direction and 10% of the outcomes are misleading in the other direction. So let's circle back to the question, the stakeholders, very natural, very, very, very reasonable question. What do we risk if we show the district program managers their outcomes? In particular, if we show them point estimates from a time series of surveys with a modest or small number of clusters. And here's what we risk. We risk confusing them a bit due to sampling variability. Certainly, we risk doing that if we don't show the confidence intervals and if we don't show a formal p-value from an appropriate survey adjusted hypothesis test for change. You could imagine the provincial level managers wanting to make a ranked list of districts, those with the highest coverage, medium, and low coverage. Those ranked lists are going to be misordered because of sampling variability. We're going to be giving some attention to places that seem to do well and places that seem to do poorly. And that attention will be allocated somewhat inefficiently. When we show a sequence of point estimates, we risk mistaking noise for a signal, and I'm using the informal phrase here that we risk chasing our own tail, but spending energy on apparent changes that are not real. So our advice is that it's great to stratify the sample. It's great to include some clusters from every health district, but if for reporting, for estimating coverage, the small samples should be aggregated up to higher levels, or they should be used as input for some model-based estimation, and that we shouldn't be reporting, we certainly shouldn't be reporting only point estimates at the district level. Now I'm going to go back to an early slide here and just be sure that we've been clear about why the results are misleading. So here's a single stratum. Here's the true underlying truth. But if we sample these, if we go to only 5 of these clusters to try to estimate coverage, when the clusters are selected randomly, there's a chance that we'll pick 5 or 7, clusters down here where coverage is very high. And so the point estimate will be higher than it should be because we've only gone to places by chance where coverage is very good. Or we may pick 5 or 7 clusters that by chance are places where coverage is very poor, and the estimate of coverage might be notably below the population average. The population average here is right in the middle, about 50%. But if we only go to clusters like these, we're going to misestimate low. If we only go to clusters like these, or if we mostly go to clusters like these, we're going to misestimate by giving a higher than appropriate estimate. And so the the issue is strongest in places where the coverage varies a lot. And then just because clusters are selected randomly, because we don't have a way of being sure that we select some clusters where coverage is high, medium, and low, we're going to see variability in the outcome. So that's the reason for the sampling variability. That's the reason that the changes can be misleading, because if in round one, you happen to select 5 clusters where things are better than they should be, and in round 2, you happen to select 5 clusters where things are worse than the average, then you have an apparent decline in overall coverage, even though what you're really seeing is just sampling variability. And this is also why when you randomly select dozens of clusters rather than fewer than a dozen, that the results are more stable. There are fewer misleading results. But if you take time to go back and look at the slides and look at the 30 clusters, which has been the WHO recommendation for a long time, 30 clusters is good, but it's not nearly as good as 49 or 64. There's still a lot of sampling variability in the rows for 30 clusters here. So I was just going back this morning and looking over these rows for 30. It's better for sure to do more than 30 if you can afford it, for keeping down sampling variability. So I'm just walking back through the slides slowly here to look at these rows with 30 clusters. There are still a lot of results here where the point estimates alone without confidence intervals would be misleading, and trends without hypothesis tests and p-values would also be misleading. For the future, what do we think? Well, we want to share this news, the results of these simulations, get them out to stakeholders, to talk with programmatic staff. Their problem, their quandary is still real. They still would like to know what the coverage is and how it's changing over time. Are the measures that they're taking being effective or not? That's a reasonable question. How can we help them do that? But how can we help them do it without misleading them? And how do they like to see the year-to-year outcomes? What are the tables and charts they like to see? And how can we clarify the role of sampling variability in those tables or charts such that they don't get confused by outcomes from small samples? And then we'll just point out again that for the kids in that sample, the survey data are signal and not noise. And so if you find some clusters where coverage is low, well, that's a signal. We know then that there are some clusters where coverage is low. And so can we narrow in on what the challenges and issues are in the areas where we did find low coverage? But it doesn't mean if you sample only a small number of clusters and you don't find any clusters where coverage is low, that doesn't mean they're not out there. Maybe they're not out there. Maybe all the clusters have high coverage, as did the 5 or 7 that you sampled, or maybe your mesh just wasn't fine enough, and you've missed the pockets of areas where kids are underserved. So that's the quandary of reporting results with a small number of clusters. Thanks very much.